Okay, so we are going to look at the Galerkin's method for the solution of one-dimensional differential equation. In this case, we have, this is the differential equation that is in general terms the solution for a problem such as the one we have been doing, which entails bending of which involves the deflection of a simple supported beam. That's what we were doing. Okay, so in this case you have a situation where we have a simple the basic equation in here. D is the dx squared y dx squared. Okay, so with the boundary conditions that we do know a value of phi at phi is equals 0, and we know also the value of h and phi equals to h. So what we need to do is to establish a concept of what we call the weighted residual integral. In other words, we are going to assume a solution for this equation in the form of a function. We'll replace that, and if we do that, then it's very obvious that there is a residual will exist, which will be 0. If we multiply by a weighting factor and we integrate it, we obtain this integration. We need to evaluate this integral. So what we need to do is to have the function in there and evaluate the weighted residual integral in there. This is the expression, the weighted residual in this case, this weighting function. We need to use the same function, or you could use a weighting function using n's of 1 and n's of j. So this weight, the Galerkin proposes to use as a weighting function in here the shape functions. That's why it was important for us to know what shape function is. So we need to use a new weighting function for each node, and we need to construct the functions as we see it. As for example, in here we have a one-dimensional finite element, and let's say we pick 3 nodes, 2, 3, and 4. And in doing that, in here we have, this is the shape function between 2 and 3, this is the function between 3 and 4. And if we write it down as a function within each element, we know that n2 that belongs to element 3 is this. And I think we'll continue the next time, all right? We'll stop now.